Okay guys, welcome back. So in the last video I gave you a brief introduction about the periodic table. So in this video I'll be explaining you about the periodic trends. So in the last video I explained to you about the characteristics and the types of classifications that we can do for the modern periodic table. So what are the periodic trends that you can see? Now actually the modern periodic classification, now the types of classifications are actually not necessary to explain you about the periodic trends. Several periodic trends can be seen in the periodic table, but these five are the most common and the most important that we categorize about when we categorize about the periodic trends. So first of all, you need to understand what is the electron configuration. Now you may have already known by now, so you need to identify as to how the electron configuration varies along different periods, different groups, and in different blocks. And the second important point is about the atomic radius. Then we'll go to the ionization energy, the electronegativity, and the electron affinity. So we'll discuss these in detail. So you know already about the electron configuration. Now electron configuration was mentioned in another video here. So now in this video I'm going to explain you as to how the electron configuration is important when you consider about the classification of elements across periods and groups. So actually the electron configuration is the basis or the base of the modern periodic table. So the due to this reason, the electron configuration of elements show a recurring pattern of the chemical and physical properties. So the electron configuration is based upon as to how the electrons fill into the last subshell, actually the last shell, and hence the last subshell. So the last electron, we also call that the distinguishing electron, is the most important component of any element, as these valence electrons are involved in chemical interactions between atoms. Now for example, if you take sodium and chlorine, you can say that sodium has a configuration of neon core and 3s1, and chlorine has a configuration of neon core 3s2 3p5. Now if you take one electron from sodium to make sodium plus, so that will become the neon core, and if you gain one electron, if you give that electron to chlorine will gain the electronic configuration of argon, right? So that will be the argon core. So sodium plus and chlorine minus, or sodium ion and the chloride ion, will together form the sodium chloride or the normal common salt crystal. So that is the importance of the last electron, right? So you can give electrons to form ionic bonds. Now I explained to you about the ionic bonds in another video. You can give electrons to form different types of covalent bonds. For example, polar covalent bonds, non-polar covalent bonds, coordinate polar covalent bonds, and so on. And you can even form metallic bonds, right? So there are different types of bonds. So bonds are only one importance of this last electron or the distinguishing electron in chemical interactions. Another importance of the last electron is when we need chemical reactions, right? For example, when we need color changes to identify elements, identify compounds, we need the behavior and actually as to how the last electron pays a contribution to these chemical interactions. So there are various uses. Now as I explained a little one or two uses, there are various uses of this last electron. Now you may have actually identified about this importance throughout the courses and throughout the theories and the modules on chemistry. So the last electron is also called the distinguishing electron, is what determines the electron configuration. So due to this reason, and due to the reason that electron configuration is the basis of the modern periodic table, electron configuration is of the utmost importance to study, right? It is very important when studying about the periodic table, right? So these electrons, as I mentioned in the first part of the video, fill according to the Mendelean rule, right? Mendelean rule, also called the Aufbau principle or the energy ordering rule. Now there are various names to explain this. So this is what I call the Aufbau rule or the building up rule or the Mendelean rule or the energy ordering rule. So you can see that you have already seen about the electron configurations of different elements. Now in the case of the fourth period, the d electrons here, you can see that 1s, 2s, 2p, 3s, 3p, 4s. Before filling up 4p, you can see that 3d electrons are filled. Similarly, you can see 4d, and when you come to the fifth group, you can see that 4f groups are also filled. So this is actually the basis of electron fields, and hence the basis of the modern periodic table, and hence the basis of the main physical and the chemical characteristics and the comparisons of elements in chemistry, right? So this is the most important concept when you are thinking about the periodic table, and the classification and the characteristics and the comparisons of elements inside the periodic table and in chemistry. So you can see that this can be explained using the atomic energy levels theory. You can show here. Now s electrons in the first shell has the least energy. You increase the energy here when you go to the s when n is equal to, so when the shell number is 2, that electron s, for example, now if you consider the last electron of helium, it's much less, it has less energy when compared to an outer electron of sodium, right? So when you go up the ladder like this, the energy increases. So you can see that the energy of 3p is greater than that of d, but d is greater than, d is in between the energies of p and s. Now actually the energy of 3s is less than that of less than both of 3d and 3p, so d falls in middle, so the d electrons we denote in the middle, right? 3s, 3p, 4s, like that, and then 3d, and comes like this, right? So that's about the atomic energy. So that was explained in another video. So another similar effect can be seen in f element. Now I was not drawn the f elements like this up to 5 or 6, right? So you can see a similar trend what you saw here for the d electrons in the case of f electrons as well. So that is about the electronic configuration. So as I mentioned a little while ago, another important characteristic that you can see, or distinguishing factor that you can see, is the atomic radius. Now we can see that the atomic radius of elements in the periodic table as follows, right? So there's a variation, a similar variation. You can see that this is like an L curve, right? L curve you can see, right? A similar, right? This is actually like a translation, right? Translation of this. Now this is one curve, this is another curve, this is another. Now this don't think about this. This is actually due to the d electrons, right? When you think about the s and the p electrons, you can see a L-shaped curve like this, right? So and this curve throughout the atomic number and the period translates like this. So you can see that the atomic radius of lithium to be smaller than that of sodium, and sodium to be smaller than that of potassium, and potassium to be smaller than that of rubidium. So what actually happens that when you go across the groups, right? So lithium, sodium, potassium, and rubidium, cesium, francium, all they are in a single group. So the atomic radius increases when you go across, or when you go down a certain group. And you can also see another important relationship between the period and the atomic radius is that now for all these curves you can see that from lithium to francium, from sodium to chlorine, from potassium to bromine, rubidium, and so on, you can see that the atomic radius decreases. Now this rectangle shape, or this compact nature, actually compacts the elements in the period 2. Similarly, you can see this rectangle compacts the elements in period 3, period 4, and period 5. So this is actually the atomic radius variation across different periods and groups. So what you can see here is that when you go when you go from left to right across a period, you can see that the atomic radius decreases, right? Atomic radius decreases. So when you go from left to right across a period, you can see that the atomic radius decreases, and when you go from up to down, right, across a group, you can see that the atomic radius increases. So the relationship between the period. So what is actually the result, right? What is the cause of this, right? What is the cause as to why when you go across a period from left to right, the atomic radius decreases, and when you go from up to down across a group, the atomic radius increases. So what is the cause of this? So there are two causes called the shielding effect of the electron shell and the effective nuclear charge. So what are these terms? So when you move from the left to right, now first of all I will consider about the decrease of the atomic radius when we move from the left to the right of a period. So when we move from the left to the right across a period, electrons are added consecutively to the outer energy shell. Now example, if you take an example, sodium and magnesium and aluminium, you can see that sodium has a configuration of neon core and 3s1, magnesium has a configuration of neon core and 3s2, and aluminium has a configuration of neon core 3s2 3p1. So when you go from sodium to magnesium to aluminium, electrons fill now first of all to 3s, and at magnesium 3s stops, and finally the distribution electron of aluminium to the 3p. So what happens is that electrons are added consecutively, right, one by one, to the outer energy shell. Now electrons within the shell cannot shield with each other from the attraction to protons, right? So what actually happens is that this is actually a shielding or a covering. Now you can see if you view this in 3D that protons are actually in the middle of the nucleus, and the electrons are like actually shells, right? Shell structures like spheres in spherical nature. If you think about the atom, these electrons are actually in parts where we can see in a spherical nature. So these spherical natures, now actually 2s covers 1s. So after 1s you can see 2s, after 2s you can see 2p, after 2p you can see 3s, 3p, and so on, right, according to the filling of electrons in the electron configuration nature. So what actually happens here is that when you go from 2s to 2p, 2p is far away from the protons than 2s. So 2s is closer and 2p is far away. So actually 2s covers 2p electrons. So this is actually a shielding or a covering of electrons by the preceding electron shells. Since the number of protons is also increasing, the effective nuclear charge, right, increases across a period. This results in the decrease of the atomic radius. Right, you can see that the attraction changes. Now a contrasting occurrence occurs in a group. Moving down a group in the periodic table, the number of electrons filled with electron shells increases. However, the number of valence electrons remain the same. The outermost electrons in the group are exposed to the same effective nuclear charge, but electrons are found farther from the nucleus as the number of filled energy shells increases. Therefore, the atomic radius increases, right? So if you take lithium, sodium, and potassium, you can see that lithium has a configuration of 2s1, sodium has a configuration of 3s1, potassium has a configuration of 4s1, and so on. So actually, if you think about the lithium or actually the alkaline series or the group 1 elements, you can see that the last electron is filled to the same orbital. Now I'm thinking about the orbital, not about the energy level. It's filled to the same s level. It is S2s1, 3s1, 4s1, and so on. So it's filled to the same s orbital, although the number of the energy level changes. So actually the number of valence electrons remain the same. Now if you take lithium, the number of valence electron is 1, sodium is also 1, potassium is also 1. Even when you go to rubidium and francium, they will also be 1. However, the number of shells increases, so the effective nuclear charge of the electrons or the effective nuclear charge effect of the electron shells contribute to the increase of the atomic radius when you go down the group. So that is about the atomic radius. So another important concept, now we actually studied about the electron configuration change, so how the electron configuration changes affect the characteristics and the comparisons of elements inside the the periodic table. So another important characteristics was mentioned a little while ago about the atomic radius. So another important characteristic is the ionization energy. Now you may have already known what is meant by the ionization energy. So ionization energy is the energy required to completely remove an electron from a gaseous atom or ion. So if you take sodium, right, if you take sodium, my popular example. So if you take sodium, you can say that sodium has a configuration of neon core and 3s1. So sodium has a valence electron in the s shell, right? So when you take that electron out by giving some energy, so when you give energy, when you increase the energy up to some level, this electron may go to the infinite energy level. So that actually this concept was explained in the concept of atomic levels or energy levels in the first part of general chemistry, right? This is just a reminder about the concept of the ionization energy. So when that electron goes to the infinite level, that is actually the limiting occasion of this electron inside this atom. When you even increase it by 1 joule, the energy is applied, this electron will get rid of the attraction, the complete attraction required. The minimum energy required to completely remove an atom attraction from the nucleus is called that element's ionization energy. Now ionization energy, as I mentioned in the other videos on general chemistry, varies for different elements because about the characteristics and actually due to the electron configuration. So it varies, and the number of subshells. Now if you take sodium, and if you compare lithium, sodium and potassium, now we can see that the ionization energy of lithium to be somewhat higher than potassium, right? So you can see it here as well, right? Lithium, sodium and potassium, rubidium, cesium, francium. It goes, when you go down the group, the ionization energy of the first ionization energy also decreases, right? So when the number of subshells increases, the ionization energy or the minimum energy to remove the valence electron, when I am talking about the first ionization energy, so the freezes down the group, right? Now you can see that the first group, now when you think about the first ionization energy, now noble gases have the highest ionization energy. So that is actually due to, now you can see that noble gases here 1s2. Now when you ignore helium, all the other noble gases has s2p6 configuration. So when you take neon, it has 2s2 2p6 finally. When you take argon, it has 3s2 3p6. When you go to krypton, you can see that it has 4s2 4p6 and so on, right? So what actually happens is that all these noble gases except helium has a s2p6 configuration. So we call that configuration to be the noble gas configuration. So when you form ions, the positive ions or the cations and the negative ions or the anions, what happens is that those elements gain the noble gas electronic configuration. So you may be well versed with the noble gas configuration. So I assume that, and when we have a noble gas configuration, we see and we can assume that this element to be of stable nature. So when you provide energy, when you provide an actually infinitesimal energy, what happens is that this electron may change, but this element or neon, argon, krypton, xenon, radon, any element, even helium, doesn't like that, right? Doesn't like. Any element wants to become stable, not to become unstable from a stable configuration. So when we actually provide energy, a huge energy to these noble gases or rare gases, in fact, what happens is that they release the outermost electron, and then what happens is that they tend to become unstable from a then stable configuration. So they don't like that. So that is the highest energy that we can obtain in a period for the ionization, first ionization energy. However, this is in complete contrast when you go to the group 1 elements. Now for example, if you take lithium, it has a configuration of helium 2s1, right? When you go to sodium, it has a configuration of neon 3s1. So neon means the neon core, right? And when you go to potassium, it has a configuration of argon core and 4s1. So these elements, when you remove this electron, this is actually the valence of the distinguishing electron. When you remove this electron, what happens is that they tend to gain the noble gas configuration. So as I mentioned a little while ago, the noble gas configuration is what we consider as the stable configuration for any element. So these elements like that, right? These elements like that. So what happens is that when you remove this electron, they tend to get the stable configuration. So they like that the stability, that they then achieve then. So what happens is that the least ionization energy is experienced. So the least first ionization energy is experienced by the first group elements or the alkaline elements. So when you go from, this is one period, right? One period. This is another period. You can see when you go from here to here, from lithium to neon, the ionization energy increases. You can also see some variation of the ionization energy here, right? So you can go up like this, then go some limiting and some recurrence of this pattern, right? This pattern is recurring all over the periodic table, or the elements of the periodic table, or the elements of different periods. All right. So that's it about the ionization energy. So that is it about the first ionization energy. Now what happens when we consider about the second ionization energy? Now this is actually a table of the ionization energies, and you can say, now you can find this experimentally. So you can see that when you take some element, say sodium, you take my popular example sodium. Sodium has a least ionization energy, or in fact it's better to take lithium, right? Lithium, because you can see some distinguishing factors. So when you take lithium, lithium has an ionization energy of 520 kilojoules per mole in the first ionization, for the first ionization energy. And when you come to the second ionization energy, what happens is that it has the highest second ionization energy. Now when you consider from lithium to neon, so this is actually the second period. So it has the highest ionization energy. Now lithium has 7297, beryllium 1757, and even neon has 3963. So the ionization energy, you can see there's a variation. However, the highest second ionization energy of the second period belongs to lithium. So you can see a similar variation of the ionization energy. So the second ionization energies for the third, fourth, and so on group periods and so on. So what happens is that when you go to the second ionization energy, now when you take lithium, lithium has already achieved the noble gas configuration. So lithium has a configuration of helium, sodium has a configuration of neon. So it has a noble gas configuration. So we consider that noble gas configuration to be the stable configuration. So it has a stable configuration. So when you remove that electron, it happens the same thing that happens to the noble gases or the rare gases for the first ionization energy. So they don't like to become unstable from a then stable equilibrium, right? So they tend to dislike that, and we have to provide the maximum energy. So you can see that if you plot a graph for the second ionization energy for different elements in the periodic table, you can see that the highest ionization energy belongs to the first group elements. And in a similar way, you can see that when you take the third ionization energy, the highest ionization energy is obtained for the alkaline earth metals or the second group elements. So that is in a similar way, it has achieved a noble gas configuration, and it dislikes to become unstable from a then stable configuration. So that is about the ionization energies. So in this video I explained to you about the different types of variations or different types of periodic trends. So I explained to you about the electronic configuration, the atomic radius radii variation, and the ionization variation. So the other two variations about the electronegativity and the electroaffinity, and some other variations and the other trends in periodic table, and a summary of these trends will be explained in another video. So thanks for watching this video, and see you then.